August 12th, 2026, Northern Spain. My goal is to be standing in the path of totality, ready to capture the best images possible of the total solar eclipse. But you don't just show up to a total solar eclipse. You need to know exactly when and where the sun and moon will be down to the second. Sure, I could go look this up on a NASA website and write down a timeline. But what if my plans change? What if the weather forces me to drive to another location? Any timeline I would have put together would be out the window. So I need to understand how to calculate the total solar eclipse contact times in order to write my own software and automate this whole process. If you wish to predict a total solar eclipse from scratch, you must first invent the universe. Imagine we are standing on the surface of the Earth, looking out towards the horizon. Let's strip away the atmosphere and the clouds. From our perspective, the sun is just a disk moving along a path. We also have the moon. It's moving along its own path, orbiting the Earth while we orbit the sun. Most of the time, these two paths miss each other completely. The moon misses the sun, and we go on about our day. But every once in a while, these paths overlap, and we can experience totality, where the moon completely covers the sun, revealing the sun's corona. So how can we predict when the moon will intersect the sun? Let me walk you through it. Imagine standing right here. We are the observer. To know where the sun is, we can draw a straight line from our eyes to the center of the sun. Then we can draw another line to the center of the moon. Now we have two lines in 3D space. These are vectors. There is a mathematical operation we can use to calculate the angle between the sun and moon. As they approach each other, the angle shrinks. The first moment when the moon's disk starts to cover the sun is called first contact. How can we calculate that? The sun takes up space on the sky. With careful observations, we can draw a line from the left and right edges of the sun. Given these two lines, we can measure the angle between them mathematically. We call this the angular size. The size of the sun measured not in meters, but in degrees. For the sun, this angular size is small, about half a degree. We can repeat this process for the moon as well to compute the moon's angular size. By amazing coincidence, the moon is about the same size in the sky as the sun. The sun is 400 times wider than the moon is, but it's also 400 times further away, so they appear approximately the same size in the sky. I've glossed over a few details. The moon does not orbit the Earth in a perfect circle. It's actually an ellipse. The moon's orbit is actually an ellipse. What this means is sometimes the moon is slightly closer to us and sometimes slightly further away. When the moon is further away, this can have a huge impact on the solar eclipse. The moon's angular size actually is smaller than the sun's. When an eclipse happens in this situation, we call it an annular eclipse. The word annular comes from the Latin word annulus, meaning ring. Another possibility is when the sun and moon are at the closest point in the sky, and the moon is on the knife edge of crossing the sun's angular size. We can get a hybrid eclipse, where we can experience totality that transitions into or out of an annular eclipse. Recall that the first time the moon covers the sun is called contact 1. There are 3 other contact events during the solar eclipse and are appropriately named contact 2, 3, and 4. Contact 2 and 3 are the most important events. Contact 2 is the start of totality, with contact 3 the end of totality. Finally, contact 4 is the last moment the moon is covering the sun's disk. If you're standing in the right location in Spain on August 12, 2026, you will experience over a minute and a half of totality. So I'm going to show you how I'm calculating contact 2 and 3, the start and end of totality. These are the most incredible and important moments to photograph. Recall that we can construct vectors from where we are standing to the center of the sun and moon. We can also construct vectors to their edges and thus compute their angular size. Half their angular size is their angular radius. Now, if we measure the angle between their centers, we have their angular separation, noted here as S. If this angular separation is greater than the moon and sun angular radius, there is no overlap possible and thus no eclipse. The moment the angular separation, S, is less than or equal to the sum of the radii, we've made first contact. If S is shrinking, we're entering the eclipse. The most critical moment for the total solar eclipse is the transition into and out of totality. We again compute the angular separation between the sun and moon. To detect the start of totality, I've rearranged the expression slightly to create a discriminator. When this expression is positive, we're in totality. After totality, when the angular separation is again equal to the sun and moon radius, we know we've hit contact 4 and the eclipse is over. Okay, I'm using a Python package called AstroPy, and in the following animation, I made a realistic simulation using the math I've shown you. This will demonstrate the critical moments of how I'm detecting the start of totality and the end. So why am I working so hard on this software? Totality. Totality is an incredible experience, and it's also very incredible to photograph. So I want to automate my camera during these stressful moments so I can sit back, relax, and enjoy totality without worrying about my camera. Thank you for watching to the end of my video. If you've enjoyed it, please smash that like button, hype the video, and subscribe to follow my journey in capturing the total solar eclipse in Spain. In the next video, I'm going to demonstrate the software I've written to do all this, and tell you about my failure during the 2024 eclipse in Texas. Thank you.